Welcome to LEMP Pharmacy Tutorial. Today we will be looking at the principles of pharmacokinetics.
So what exactly is pharmacokinetics? Well, put simply, it's the science of what the body does to a drug. Think of it as the complete story of a drug's journey through you. And this journey always has 4 key stages, which you can remember with the acronym ADME. That's A for absorption, getting it into your system, D for distribution, sending it where it needs to go, M for metabolism, breaking it down, and finally E for excretion, getting it out again.
So here's our game plan for today. We're going to start with why any of this matters in the first place. Then we'll look at how we actually model a drug's distribution. After that, we'll dive into the big 3 parameters: volume of distribution, clearance, and half-life. We'll see how they all work together to achieve the ultimate goal of steady state. And of course, we'll wrap it all up with a quick recap of the key principles.
Right, let's kick things off with the big why. It's so easy to dismiss this stuff as just, dusty textbook theory, but it's not. These principles are the absolute bedrock of safe and effective medicine. Honestly, getting this right is the difference between a drug being a cure and it being a poison.
Now, the human body is, let's face it, incredibly complex. So to get a handle on it, we have to simplify things. We use mathematical models to make a drug's journey predictable. But you might be asking, why bother with all the maths? What do these models actually help us do in the real world for a real patient?
Well, they do a ton of heavy lifting for us. These models give us the power to predict drug levels for any dose we can think of. They let us calculate the perfect, optimal dose for an individual, moving beyond that one-size-fits-all idea. Here's a big one. They help us estimate if a drug might dangerously build up or accumulate over time. They also let us correlate what we measure in the blood with the drug's actual clinical effect. They're also used to evaluate if a generic drug really is the same as the brand name version. And it doesn't stop there. They can show us how a disease might totally change a drug's behavior, and finally, help us predict and avoid dangerous drug-drug interactions. To do all that amazing stuff, we have to start with a pretty bold simplification. We basically pretend the body isn't this messy, complicated collection of organs and tissues, but instead a neat series of simple, distinct compartments. Now, this is a really crucial point. When we say compartment, please don't picture a little box floating around inside you. It's a completely imaginary concept. It's a tool. We group different tissues together based purely on how they behave. If they have similar blood flow and a similar liking for a drug, we lump them together. It's a kinetic space, not a physical one.
The simplest way to do this is the one-compartment model. Here, we pretend the entire body is just one big container. Imagine dropping a bit of dye into a bucket of water. It mixes almost instantly, right? This model works great for drugs given as a quick IV shot, where they hit the bloodstream and distribute almost instantaneously. And when you track the concentration, you get this lovely, simple, straight line heading downwards on a graph. That line means one thing and one thing only: elimination.
But of course, the body is way more complicated than a single bucket. So for most drugs, we need to level up to the 2-compartment model. Here, we have a central compartment, the blood and well-supplied organs, and a peripheral one for tissues the drug gets into more slowly, like muscle. And wow, look at the graph now. It's completely different. You see 2 distinct phases. First, this really steep drop. We call that the alpha or distribution phase. Now, listen closely. This is not the drug leaving the body. This is the drug moving rapidly out of the blood and into the tissues. It's only after that initial rush that the curve flattens out into the much gentler beta phase. And that shows us the true, slower rate of elimination.
And this isn't just an academic point. This is where things can go seriously wrong in a hospital. Imagine you take a blood sample during that steep alpha phase to check the drug's half-life. You'd get a dangerously wrong answer. You'd think the drug is being cleared out incredibly fast, and you might calculate a maintenance dose that's way too low, basically setting the patient up for treatment failure.
But what if a drug is, extra sneaky? What about drugs that like to hide away in deep tissues? For those, even 2 compartments isn't enough. So we bring out the 3-compartment model. This adds a 3rd deep tissue compartment for places with really poor blood supply, like bone or fat, where a drug can go and settle in for a very long time.
The danger here is a bit of a silent threat: sneaky accumulation. With each dose, the drug can slowly build up in that deep tissue compartment, even while the blood levels look perfectly normal. This can lead to delayed toxicity, side effects that might pop up weeks or even months after a patient has stopped taking the drug. It's like a hidden reservoir that can cause trouble way down the line.
Okay, so we've imagined these compartments. That's great, but how do we put a number on them?
How do we make this idea useful? Well, that brings us to our first key parameter, the volume of distribution, or VD for short.
Right, I really need to hammer this point home. The volume of distribution is not a real physical volume inside a person. The definition uses words like hypothetical and apparent for a very good reason. It's a calculated number, a piece of mathematical fiction, if you like. But it's a fiction that tells us a very true and very important story about how widely a drug is spread throughout the body.
And you might be surprised at how simple the formula looks. It's just the dose you gave, divided by the concentration you measure in the blood plasma. But don't let that simplicity fool you. The number you get from this simple equation is an absolute powerhouse of information.
So let's look at the two extremes. If you get a low VD, that tells you the drug is basically stuck in the bloodstream. It's probably a big molecule, or it's tightly bound to proteins in the plasma. A great example is warfarin. Now let's flip that. A high VD tells you the complete opposite story. The drug has fled the bloodstream and is now hiding out, concentrated in the body's tissues. This means the concentration in the blood is tiny, which makes the calculated VD enormous. It can even be a number that's way bigger than the person themselves. Digoxin is the classic example of this.
Okay, I can hear you thinking, this is all fascinating, but it's a hypothetical volume. How on earth does this actually help a real patient? It's a fair question.
Well, its number one job, its most critical application, is for calculating something called a loading dose. See, for some drugs, it could take days, even weeks, of normal dosing to build up to a level where it starts working. And in an emergency, you just don't have that kind of time. A loading dose is a big, one-off, initial hit designed to fill up that entire apparent volume all at once, getting the drug level up to where it needs to be immediately. And the formula for it makes perfect sense. You take your target concentration, multiply it by that volume of distribution, and then you divide the whole thing by the drug's bioavailability, or F. Now, F is just a fancy way of asking what fraction of the drug I took actually made it into the bloodstream. For an IV drug, it's 100%, so F is 1. For a pill, it'll be something less than 1. Let's walk through a quick example together. First, we gather our intel. Let's say we have a drug with a massive VD of 500 liters. Its oral bioavailability, F, is 0.75, and the target concentration we're aiming for is 1.25 milligrams per liter. Okay, got our numbers? Now we just pop them straight into the formula. That's 1.25 times 500, and all of that divided by 0.75. You run the numbers and boom, 833 milligrams. That is the precise dose needed to fill that huge apparent volume and get the drug working straight away. It's a perfect example of taking this abstract theory and turning it into a practical, potentially life-saving action. Right, so we've gotten the drug in, and it's distributed throughout its compartments. Now what? Well, now the body's own cleanup crew gets to work, and this brings us to clearance and half-life.
Clearance is all about efficiency. It's not about how much drug is being removed. It's about the volume of blood that gets completely scrubbed clean of the drug every hour. Think of it as a measure of how good the body's machinery, mostly the liver and kidneys, is at its job.
Now, clearance is a bit of a technical concept, but it gives rise to something much more intuitive, the half-life. This is simply the time it takes for the amount of drug in your body to drop by half. And what's its most practical use? Well, it's the main thing that determines if you need to take a pill once a day or 4 times a day.
Let's just watch it happen. Imagine you start with 100 milligrams. You wait for one half-life to pass, poof, you're down to 50 milligrams. Wait another half-life, now you're at 25. Another one, and you're at 12.5. It just keeps having over and over again.
Now, there's a really important fork in the road here. Most drugs follow what we call first-order kinetics. That means the body removes a constant fraction, say 10% of the drug every hour. The more drug there is, the faster it gets removed. But then you have a few oddballs, like alcohol, that follow zero-order kinetics. Here, the body removes a constant amount, say 10 milligrams every hour, no matter how much is floating around. This usually happens when the body's elimination system is just completely overwhelmed and can't work any faster.
Okay, so we've got this constant tug-of-war going on, right? Drugs coming in and distributing, and drugs being eliminated. For any medication you take long-term, the whole goal is to get those two forces into a perfect, stable balance. We call this steady state.
Steady state is the therapeutic sweet spot. It's that beautiful point of equilibrium where the amount of drug you're putting in with each dose is perfectly matched by the amount the body is clearing out. The concentration isn't perfectly flat, of course, but it bounces up and down within a predictable and, most importantly, an effective range.
So how long does it take to hit this sweet spot?
Well, there's a fantastic rule of thumb for this. After just one half-life, you're already 50% of the way there. After about 3.3 half-lives, you're at 90%. But the magic number we're really looking for is 5. For all clinical purposes, we say that after about 5 half-lives, you've reached steady state. When you strip away all the complex maths and biology, it all comes down to one simple, elegant equation. Rate in equals rate out. When you've achieved that, you've achieved therapeutic success.
Whoa, okay, that was a lot, I know. We went from imaginary spaces all the way to real-world dose calculations. So let's just take a breath and do a quick-fire recap of the absolute must-know points from today.
1. We use compartment models to simplify the body's complexity so we can predict what a drug will do. 2. Volume of distribution, or VD, is that key hypothetical volume that tells us where a drug is gone and is essential for calculating a loading dose. 3. Clearance is our measure of the body's drug-removing efficiency. 4. Half-life is the practical result of clearance, telling us how often to dose. And finally, 5. Steady state is the goal, that perfect balance where drug in equals drug out, which we usually reach in about 5 half-lives.
So, there you have it. That's the story of what the body does to a drug after it's already inside. But that kind of leaves a huge question just hanging in the air, doesn't it? How does the drug get from, say, a pill into the bloodstream to even begin this whole journey? That is the other half of the story.
Next episode, we will be talking about biopharmaceutics. Be sure to join in.